Okay, and we'll go to the whiteboard, and let me get, okay, this is in chapter 12, I take it, right? Is that what you meant? Chapter 12? Jalen? Jalen, can you? Yeah, okay, right. Was that chapter 12 that you meant on the homework? 12.1, 12.2, 12.2, okay. All right, and number 1, okay. Let me do some adjusting here. You can't see it, but I can. These toolbars they put in the whiteboard, so I can't write everywhere I want to. You don't see them, but I do, and that prevents me from moving them where I need to. Yeah, okay. So, all right. Toolbars are out of the way. Let me scoot the whiteboard over just a little bit so that we can get maximum use out of it. Up and over. Okay. All right. That's there. And you want problem set 12.2, right? So this is page 324. This is problem set, or problems 12.2. Put a page here, a period there, and it's number 1. All right. Now, reading what they got. A packing crate is 2.5 meters by 0.8 meters by 0.5 meters. Okay. Now I'm kind of going to try to draw this for you. Now this is going to be pretty pathetic, but maybe I can use the line draw here and maybe make it a little less pathetic. Okay. Okay, we'll call that 12.5. That's not horizontal, but it's close. Or 2.5 meters. And we'll go 8 meters deep. So 8/10 of a meter deep. So I'm just going to guess something like this. Okay, and then I'll do my best to mirror that over here, but it's probably going to be pretty poor. Yeah, it isn't very good. Okay, let me scoot this a little bit that way. Okay, and then let me yes. Okay, there is the base of it, kinda, not quite a rectangle, but close. Okay, and then the 0.45 is going to be pretty close to vertical. Okay, we'll just guess that's 0.45 and guess, I wish I could just duplicate it. Wait a minute, let me get Manasseh in. All right. All right. Manasseh is here, coming in anyway. So that's 4 students so far. Okay. Let me try to, where's my device? There it is, somewhere. There it is. Okay. I'm going to do another thing upward like that. And one more here. This is probably a waste of time, but I thought it would be better to have a visual. Okay. Okay. And there. Whoops. Something like that. Okay. Not very regular, but it's supposed to be rectangular. Okay, this is 2.5 meters here. Oops, that won't work, will it? Okay, go back to the draw mode here. Okay, whoops, this is ugly. 2.50 meters long, 0.8 meters this way, 0.80 meters, and that's hard to read, but hopefully you got what we're doing. And the height here is 0.45 meters. Okay. Now, just a thing to note here, 3 significant digits here, but only 2 here and here. So we're down to 2 significant digits. Okay. That's the packing crate, and it weighs, and this, by the way, weight is a force. So this force due to weight pulling downward on it, okay, is 1.41. That's supposed to be a 4, doesn't quite look like 41 times 10 to the 5th newtons. That's a 10 to the 5th newtons. That's a force, weight going downward. Okay. Find the stress in kPa, kilopascals, exerted by the crate on the floor in each of its 3 possible positions. I'm not about to draw the 3 possible positions. I did poorly, but still did it just to get this one. Okay? Now, here's what we'll need to know. First, the area of the top here and the bottom. I'm just going to call this area of top and bottom, T/B. That's what that stands for, top and bottom, is multiply the 2.5 by the 0.8. Okay? So let me get my calculator. Okay. All right. So 2.5 times 0.8. That area is 2. I should have done that in my head. Okay. That's 2.0 square meters. Now that says it's sitting here. That's a squared meter. I didn't leave enough room up there. Okay. Now, this end panel over here, I'm going to call this the right side. The area of the right and left sides, that's R/L if you're trying to figure out what that is, that would be 0.45 times your 0.8. So 0.45 times 0.8, that would be 0.36 square meters. 0.36 square meters. Now, is this making sense so far? Okay. And then the one other dimension we don't have is the area of the front and back, the way it's sitting here. Because these are supposed to be the same. My drawing doesn't look like it, but they are. And that's 2.5 times 0.45. So that's 2.5 times 0.4, whoops, that didn't take. 2.5 times 0.45. that gives me 2.25. Now that's really too many significant digits, but I'm going to be okay with that. I don't believe it though. Let me try that again. 2.5 times 0.45. That didn't take. 2.5 times 0.45. Yes, 1.125. Okay, 1.125. Now I admit, too many significant digits there, but this isn't your final answer. This is an intermediate step. So I'm going to leave those digits in there, and that would be the area of what right now is your front and back. Okay, now what they're asking for here, the stress in kilopascals exerted by the crate on the floor in each of the three possible positions. Now this first one that I have here is the top bottom, because the bottom's on the floor here. And what is your stress? Your stress is force per unit area. And your force is 1.41, if I can read my ugly writing there, 1.41 times 10 to the 5th newtons divided by, and the area of the top or the bottom, and it's the bottom that's on the floor now, is 2 meters squared. Okay, so that would be 2, I'll put 0.0, I don't need to but okay, meters squared. And let's see what that gives us. 1.41 times 10 to the 5th. So I'm going to have to turn my calculator or my phone to the side now to get scientific notation. So that's 1.411. Okay. Now, scientific notation is the EE key. The capital E key, somewhere right around there. There's too much glare. There it is, right there. EE key. Okay. EE 5. Okay. Divided by 2 equal, that's 70,500 pascals, right? Now, because a Newton per square meter is a pascal. So that's 70,500 pascals. Okay. Now, at best, maybe the 5 is significant. I really don't think so, but we'll see what the book says. Okay. This is, oh, I didn't put my units down. Shame on me. Pascals, PA. Okay. And that would be, to get it to kilopascals, move the decimal 3 places, and you got 70. It's either 71 or 70.5. Now, I don't know how picky they're going to be on the significant digits. Technically, I don't see that's more than 2 significant digits. Do you have the answer in the back of the book? That's all right. I can look it up. I've got it marked, I think. I thought maybe you had it right handy. Okay. It's either 71 or 70.5 kilopascals. Let's see what we got. 71. Okay, so they rounded up, and I thought they should have, but okay. So let me erase that and make it 71. Okay. 71 kilopascals. That's when it's on the big side. So I'm going to call that the stress of the big side on the floor. Okay. Now the next biggest side would be if we turned it so the front and the back, front and back, that they are on the floor. So we're going to flip that this way, one rotation. So what I'm calling front back is now going to be top bottom. That's going to be on the floor. So this will be the medium one. the stress on the medium side, the middle stress, okay, the middle side on the floor, okay, that's going to be the same 1.41 times 10 to the 5th, because it's the same weight, the same force, newtons, pretty ugly N, okay, pretty ugly, that doesn't make sense, divided by the area on the front back side, the way it's now sitting, that would be 1.125. 1.125. Now again, that's too many digits, but I don't ever round until the very last one, and that's meters squared. So let's get the calculator wherever I put it. There it is. Okay. 1.41 EE5. Now, was that someone trying to get in? I wasn't paying attention. I hope it wasn't. Let me just see if anyone's waiting, because that thing came up. No, we still got 5 people, and for some reason that changed, so let me go back to the screen here. Yuck! Why did it kick me out of the meeting? This is so aggravating. I can't get back in. Can y'all hear me? Anybody? You can. Okay. Okay. So it must not have kicked me out of the meeting, but it gave me the thing that I had to do to return to meeting. And now we've got to get these things out of the way again. All right. Oops, here's Mercy is waiting. So let me get Mercy in. So I must have been psychic, thinking Mercy was coming. Okay. There's Mercy. So now we've got 5 students, and let me make sure that's what we've got. I see 4 plus Mercy is 5. And that's also what we got down here, right? Yeah, I'm the 6th one. Okay. Okay. So going back to my calculator, that was 1.41 EE5 divided by 1.125. 1.125 equal, and that gave me, I got 125,333. That's pascals. Now that's too many digits, I know. Okay, but it's 125,000, and then it says 333 pascals. I'm going to just round that to 000 pascals, but when they do it to kilopascals, actually that becomes 130, because you only have 2 significant digits here, because this side here was 3, but this length here was 2, so that's 130, and when you get to your comma stop, that's where your decimal is now, kilopascals. Is that what they had in the back? Yes? Okay. Now that's the middle size side, but it's a much bigger pressure because it's on a smaller area, same weight, smaller area. Now the small side, which will be this side here, the 0.36 square meters, okay, that's 0.45 times 0.8. I'm calling this the small side, but it's going to be the biggest pressure or stress, and that's your same 1.41. Oh, by the way, Mercy and Manasseh, when you came in a little later, we're working example 1, problem 1, and problem 12.2 on page 324, okay? And that's times 10 to the 5th, same as before. I can't write. 10 to the 5th newtons divided by, this time, that small area is 0.36. Okay, I think you're going to be maybe a little surprised to see how the stress has gone up. 0.36 square meters. Okay, get your old calculator again. 1.41 EE 5 divided by 0.36 square meters, and that gives me 391,000 and change pascals. So I'll write it down like I did before. I don't have much room, so let me write it under here. That would be 391. It's really 392,000. There's no reason to round there, but just to get it, and that would be 1,000 pascals. I've already rounded that part, but I rounded too much. But just to give you an idea how that happened, if you had 3 significant digits, that would be right. We only have 2, so that would be 390,000. 390 kilopascals. The K takes the place of the 1,000 there, kilopascal. And is that what he had in the back? Yes? Okay. So you see the stress on the floor by the same packing crate. If you lay it flat, it's still a pretty good stress, 71 kilopascals. Put it up on the middle edge and it jumps up to 130 kilopascals. Put it on the small edge and it jumps all the way up to 390 kilopascals. That's how much stress that crate's putting on the floor. Same crate, but it just depends on the surface area. That's your spike heel on your toe. This is the tennis shoe heel on your toe, okay? The pressure, the stress is much less. Okay, did that answer what you needed?
Yes, sir, it did. Thank you.
All right, glad to. Good question, by the way. Okay, let me plug my phone back in. I might need it again, but in the meantime, I'll plug it back in to let it recharge. Excuse me. All right. Any other questions before we get going where we left off last time? Anybody? Good deal. Okay. Now, I think where we left off last time, at least where my book was, is talking about Hooke's law. Whoops, here comes somebody else, but they blacked out their name so I can't see it. Mika is here. Good deal. So Mika is here. Now, I do have sort of a dumb question for you. At least it's dumb in my book, but I want to make sure I'm thinking the same way y'all are. I got an email, received it this morning. It was either sent yesterday or this morning, stating that a student had claimed he had been attending this class. It was Christopher Nicholas Nees. Do any of you ever remember him being in the class? I know I called his name several times, but do you ever remember his being here?
No, sir.
I sure don't either. So I went back and checked. Sure enough, never had an attendance in my grade book. I checked all my emails, never had an input from him there. I'd already checked the Blackboard messaging, never any word from him there. Hadn't turned in any homework assignment, had not turned in either test. So I sent that back to the registrar's office and said, nope, this is what I got, and I copied everybody who had involved with it on that. But I just wanted to check with y'all to say, oh yeah, I remember he was here one day. I didn't have him here one day, but I just wanted to check. Okay. So, where we were was bottom of page 320, chapter 12, matter. 12.2 is talking about properties of solids. I'm pretty sure it is. It's a fairly long section, properties of solids. And we're talking about Hooke's law. Now they have a little blurb here on Robert Hooke. He was a chemist and a physicist from England. He formulated the law governing elasticity. Just give you a little bit of other background. He was a very well-established scientist when Newton was a young whippersnapper, just coming into his own. And I think that he and Robert Hooke just didn't get along very well. Hooke was well established. Newton was a newcomer on the block, but Newton was blowing everybody out of the water, okay? Everybody. And he started getting more attention. I don't know what the deal was. I know he didn't care much for Hooke, and I think Hooke really resented him. I don't know that for sure, but that's my impression. So that's about the same time we're talking about. And one of the most basic principles related to the elasticity of solids is Hooke's law, named after Robert Hooke. And let me go back. I'm pretty sure this is not on the let me just see if maybe it is. That's what we were dealing with. That's basically our packing crate on the surface that we're just dealing with, 3 different orientations. There was our compression, another form of compression, stress, shear stress. We talked about that. And there's the shear. Here is the torque, is the twisting motion, and there's that's represented. And here's the bending motion and what's represented there. And there's another bending. So that's where we left off. Let's see. Yes, here it is. I was wrong. This illustrates, let me go from current slide. This illustrates Hooke's law, okay? Anytime you're in this straight region here, now what you have here, and this always bugs me the way they do it, but it works out better that way. Here's your applied force, which to me should be on the horizontal axis, and this is the change, the deformity that happens, the change of length or change of whatever that you're dealing with. You apply a little bit of force here, and you get a little bit of deformation. More force, more deformation. But it's always proportional. This is that straight line proportionality. Up here it begins to bend a little bit, but that's what they call the elastic region. You apply a little force, it deflects a little. More force deflects a little more. But the point is, it always springs back to the original shape. However, there's usually some limit up here where it won't spring back anymore. Now, the best example I can think of, though I'm sure there's several of them, have y'all ever broken down a ballpoint pen and you had that little spring in the top that, you know, is what pops it back and forth for you? You know what I'm talking about? A little bitty spring. You know, okay. Now, if you've ever played with that very much, you know you can stretch it a little bit and it'll go back to its size. You can compress it a little bit. In fact, you can compress it probably a lot and it goes back to its size. But if you keep playing with it and stretch it a little too far, it doesn't go back. Then you pass the elastic limit. Now you're in the plastic region. It'll never go back to that elastic region. Now, if you continue pulling on that spring, you almost get it into a straight wire, and keep pulling, at some point it's going to break, and that's called the fracture limit. That's where it actually breaks. Anything in between, it doesn't come back to its original shape. That's the plastic limit, and this. Well, Hooke's law governs this, and basically it says the applied force is proportional to, and the Hooke's law constant is usually K. Applied force is equal to K times your delta L. Okay? Now the way they express it in the book is just a little bit different. They say F over delta L is equal to K. In other words, the ratio of the applied force to the displacement here in this region only, not up here, but in this region only, that will be a constant K. When you get up here, it no longer is. anytime you have a straight line or almost straight line here, that represents a constant proportion. This is anything but a constant proportion. This is weird, okay? Nowhere close. Okay, so that's Hooke's law. That leads us to example 2, and let's go back to the whiteboard to do example 2. Now, all right, to clear the problem 1. Okay, now who was it that came in last? Was it Mercy? No, it was Mika. Mika, what this represents here is example 1, or problem 1 in problem set 12.2, one page over on page 324. Probably the best idea is wait until this loads onto YouTube video and watch it on the YouTube, and we'll talk through all that there. It's too much to go back and cover it all now. Is that okay?
That's fine.
All right, so I'm going to clear the drawing then, and let's do example 2. Now let me write, well, I'll write it down later. Okay, a force of 5.0 newtons, that's your applied force, and we'll just call it F. 5.0 newtons, which by the way represents just 2 significant digits. 5.0 newtons. They had been using 3 most of the time, but the last couple of problems have only been 2. No, I'm sorry, that's 5.00 newtons. They're back to 3 significant digits. Okay, anything after the decimal point is significant, any 0 after it. Okay, is applied to a spring whose elastic constant is 0.25 newtons per centimeter. So the K, the elastic constant, often called Hooke's law constant, K is equal to, now here's an interesting thing here, 0.25 newtons per centimeter. And I'm not used to seeing that, 0.25, if I could, my pen would write, 25, is it 250? Yeah, 250 newtons per centimeter. A lot of time you'll see that newtons per meter, but this is newtons per centimeter. Okay, let's see what the problem says. Find its change of length. So here we're looking for what they called delta L. Delta means difference in or change in length. Change in length. Now to remind you, what was Hooke's law? Okay, I said it one way, the book gave it another way. They're both equivalent. One is the way I said it was F is equal to K delta L. Okay, that's supposed to be a delta, meaning difference. The way the book gave it was F divided by delta L, which is the same thing, just divide both sides by delta L, and that's equal to K. Neither one of these fits what we're looking for here. We're looking for delta L. And actually my form is easier to get delta L. All you do is divide both sides by K. Hooke's law constant. And basically you have right there 3 equivalent ways to express Hooke's law. Here's one, F is equal to K delta L. Here's the second one, F over K is equal to delta L, and F over delta L is equal to K. So we're going to use this one, which is going to be F over K. Now, plugging in what we know, that's F is 5.00 newtons. Oh, that's an ugly 0. That's not much better. Newtons divided by K, which is 0.25 0 newtons. No, newtons per centimeter. Now, at first I was going to say we have a problem, but no, we don't, because they didn't specify what unit delta L is in. You don't have to go back to meters unless the problem says to go back to meters, or unless they give things that are in that. Now, let's deal with the units first. This newton will cancel that newton out, and that gives you basically no units here. We'll just call it 1 over centimeter. Well, let's deal with the units first. 1 divided by 1 over centimeter is the same as 1 divided by 1 over centimeter, which is 1 times centimeter over 1, which is centimeters. That's going to be a great measure for your delta L. So let's do with the units, the numbers. So we know the unit is going to be centimeters. 1 over centimeter is a centimeter. Now, 5 divided by 0.25. I'm going to do a little monkeying around here. I'm going to move this decimal 2 places this way and this decimal 2 places that way. This is just to make it easier to do our division. And that gives you 25 into 50 would be 2, and 25 into 0 would be 0. So that gives you 20.0 centimeters. 20.0 centimeters, that would be the extension. Now, hopefully they leave it in centimeters. Let's see what they do. Yes, they do. They left it in centimeters. Now, your calculator will do the same thing, but it probably won't put the 0.0 there. You need to have the 0.0 because this is 3 digits, that's 3 digits, so you need 3 digits, 20.0 centimeters. Any questions on that one? One example of Hooke's law. Okay. All right, to move on to example 3. I hear no objections, no questions, so I'm going to delete this. Is that okay? All right. Now, this is not going to give us quite enough information. Here they say a force of 3 pounds, 3.00 pounds. So here's a force, and I almost want to call it force 1 because I think I know what's coming next. Force of 3.00 pounds. That means 3 significant digits here. 3.00 pounds. Stretches a spring 12 inches. That's going to be your delta L, the amount of stretch. Delta L is 12 inches. Wow, that must be a slinky. Okay, 12.0 inches. That's quite a stretch for just 3 pounds. Maybe it's not too bad, I don't know. Okay, must be a pretty big spring to be able to stretch 12 inches. Now, what force is required to stretch the spring 15 inches? Okay, so the question is, that's why I said I want to call this force 1, and that stretches delta L1. Now they're asking what force 2, or new or different, I'll just call it 2. This is now your unknown. Okay, that's what we don't know. But now we have a new delta L, and the new delta L is 15 inches. 15.0 inches. Now, anyone have a suggestion on how we can solve this problem? Okay. This is enough information here to determine Hooke's law constant, the K. So let's do it. Now we'll use the book's definition this time and do F sub 1 over delta L sub 1. The ratio of that is going to be the Hooke's law constant. Now the reason we can do this, it's the same spring between here and here. Okay, so this will give you K. See, that's what we don't know, or else we would be able to solve this. So let's plug in what we know. 3.00 pounds divided by 12 inches. 12.0 inches. All right. So the Hooke's law constant for this will be, well, 3 divided by 12 is 3 is 1/4 of 12. So that's going to be 0.250. That's your K. This is pounds per inch, which is force per length. It's pretty ugly. Pounds per inch, and that's your Hooke's law constant. That's equal to your K. And because this is the same spring here that it is there, okay, the slope is still the same. The Hooke's law, you're still in this range. Then we use my formulation of it, which is F is equal to K times delta L. These are all same representation of the same concept, just different way of expressing it. Okay, and we know the Hooke's law constant is 0.250 because it's the same spring. 250 pounds per inch, and this will illustrate why the units are important for you. Pounds per inch okay, multiplied by 15 inches. Your delta L here, this is delta L2. This is delta L2. Multiply this by 15 inches. 15.0 inches. And this indicates that you must be doing it right, because notice your inches cancel out. One's in the denominator, one's in the numerator. And then pull out your handy dandy calculator. Okay, and that's going to be 0.25, oops, yeah, 0.25 times 15 equal 3.75. Is that what you got? Should have done that in my head. 3.75 pounds. That's how much force you need to stretch it that. 3 significant digits, because everything else had 3. Now, always a good idea with a problem like this, go back and see, does this answer make sense? So 3 pounds stretched at 12 inches, does it make sense to stretch 15 inches? You're going to need a little bit more weight. And 3.75 is just a little more weight. So yeah, that makes good sense. 3/4 of a pound more to stretch it that extra 3 inches. And let's see how the book did. Yes, they got it right too. 3.75 pounds. Okay. Ready for example 4? Okay. Example 4 is, can I go on and clear this out of the way? Okay. Clearing the, ooh, I don't know why that did away with my, okay, screen sharing pause. I don't know why that happened, but let me get it back. Okay. I don't know what happened there, but something did. Example 4. A support column is compressed, a fairly small amount, but it is compressed, 3.46 times 10 to the minus fourth meters. Okay, so there's a column, and you've got something really heavy on top, and it's going to compress that a very small amount, 3.46 times 10 to the minus fourth meters. And you expect it to be pretty small. Okay, so that's your delta L. Okay, your delta L here, the change of length here being compressed is 3.46 times 10 to the minus 4 meters. Now let me just give you an idea of what that is. Remember, if we take this decimal and move it 4 places that way, that would be 0.000346 meters. Well, a thousandth of a meter is a millimeter. And a millimeter is approximately the thickness of a dime. Okay? This is 3/10, or about a third of a dime in thickness. So that's not compressing it very much, but it is compressing it about a third of a dime's width, approximately, just to give you an idea. Under a weight, and that weight is going to be your force. Okay? So here's your force due to weight, F sub W. This book, in this chapter, they're leaving off the sub W, but I like to still put it in there. Of 6.42, it's a pretty strange looking 6.42 times 10 to the fifth, a huge weight, 10 to the fifth, that's in the 600,000 Newton range. Newton. Okay. Now, how much is the column compressed? So again, we've got, this is the given, compression 1, force 1. Okay. And then they're asking how much is the column compressed. So here will be a delta L, but this is a second one. This is a different delta L, delta L2. That's the unknown, because they're asking how much will it be compressed. That's your unknown here. Under a weight of a bigger weight, this F sub W2, or maybe I just should call it F sub 2, but I've already put the W before. F sub W2, that's not your tax information, that's something else. F sub W2 of 5.80 times 10 to the 6th newtons. Now basically 10 to the 6th means million. So this is 5.8 million newtons. This was 642,000 newtons. So it's almost a factor of 10 difference. So I would expect almost a factor of 10 difference here, going in the other direction. So let's see what we get. Again, this information here is only here to give you an ability to calculate Hooke's law constant. And what is that? F sub W1 over delta L sub 1. That will give you Hooke's law constant. It's the same column, so you don't need to call it a K1. That's just a K for this column. And let's see what that is. That's 6.42. You're going to find this is a huge K. 6.42 times 10 to the fifth newtons divided by 3.46 times 10 to the minus 4 ugly 4 meters. Last time we were dealing in centimeters, this time in meters, or 2 times ago. Okay, so what does that give you for Hooke's law constant? A huge
Like
number.
1 billion?
Yeah, I would say on the order of that, maybe even, yeah, you're absolutely right. Let me get my calculator doing, you beat me to it. My phone, it is. Okay, so 6.42, but you're absolutely right. Oh, I've got to turn it sideways. 6.42 EE 5. It didn't take the EE. There's the EE 5 divided by 3.46. 3.46 didn't take that either. 3.46. Got it. EE -4. Now mine, I have to press the 4 first and then change the sign of the 4, and that's the plus minus. So if you're using a phone, you probably have to do things sort of in backward, okay, and then we'll press equal. There's Hooke's law constant. You're absolutely right. About 1.86 approximately. Now, just because I like to carry around a few extra digits until my final answer, I'm going to mark that as, and there's no real reason for this except I just like to do it, 1.8, and you're absolutely right, almost 2 billion. 1.85, this is way too many digits, but I'd rather have them than not. 1.855. The reason I went that far is you see the next thing to the 4 is a 9. That's really close to 5, okay? And then what's the scientific notation on this? Like you said, billion, that would be 3, 6, 9, 10 to the 9th, okay? Which you also get, by the way, and this will be newtons per meter. Newtons per meter. Now, let me show you this. You take the number here, 6.42, divide it by the number here, 3.46. That's not quite 2, but pretty close to it. And this is 1.85. Okay. And what you do with your exponents, you subtract the exponents. 5 minus a minus 4, or minus a minus is plus, 5 plus 4 is 9. So that's where you get this number, 6.42 divided by 3.46. That gives you approximately that number, and then your exponents are 5 minus a minus 4, which is 5 plus 4 is 9. So that makes you feel real good, warm, and fuzzy. Now, this time we're looking for delta L, 2, okay? Now, I don't know if you remember that formula from before, but remember my rendition of Hooke's law was F sub W2 is, that's ugly 2, is equal to that K, that 1K we have, it's the same column, times delta L. And this will be delta L2. Well, this is what we're looking for, so we're going to solve for that, and we do that by dividing by K. Okay, and you see, ooh, that's ugly. The K's go out, and so delta L2 is equal to this new force, 5 point, okay, now, here's what I'm going to do, and this is just because I like to do it. I'm leaving every one of those digits on there, but what I'm doing, because we're dividing by K, I'm going to come over here on my calculator, and you see this key right here that says 1 over X, I think it is. Yeah, 1 over X. that's what I'm going to do here. This number here is my x, really a k, and 1 over k would be that. So 1 over k would be, so I'm going to press that key. You don't have to do it this way. You can write it down and do your division just like you normally would. But I'm going to do 1 over k. That makes an incredibly small number. Look at all those zeros. And then multiply that by that new force, which is 5.80. I'm just going to do 5.8 EE, and this is 6 equal. And I get 0.003131. And since this is my final answer, I will round this significantly to 3. The third digit is a 2, but look to its right, and I got a 5. That's going to round that up to a 3. 0.313 is 0.00313, and the units, whoops, sort of messed that up a little bit, didn't I? I didn't write it out. This is 5.80, and you can punch in the calculator and do it, times 10 to the 6 newtons divided by, that's really ugly writing, isn't it, 1.8. I'm sure the book rounds that to something like 1.86, but I'm just going to keep it a 555 because I enjoy writing 5. No, I'm just kidding. Times 10 to the 9th. And that would be newtons per meter. Okay, and here the newtons cancel out. Okay, and 5.8 divided by something around 2 is going to be something more than 2.5, and that's going to be your 3.1. So that's going to be, and then you see it's 10 to the minus 3, because 6 minus 9 is negative 3. Move it 3 places here. That would be 3.13 times 10 to the negative 3. And that would be meters. Okay? So this answer would be meters. Or if you do it in scientific notation, which my calculator doesn't, but I just did it for you, move that 3 places here, and that would be 3.13 times 10 to the minus 3, and that's what you get by doing your exponents here. That would be measured in meters. But do you know what 10 to the minus 3 is? 10 to the minus 3 meters? That's a millimeter, the thickness of a dime. So this now would be 3.13 dimes. That would be 3 and about 3.13 millimeters. You don't have to change it, but just to get it into something you're familiar with. That'd be about 3 and between a tenth and about 3 1/8 dimes. Okay, just to give you an idea. That's going to compress it a little bit more. Up here, this is only compressed about a third of a dime. This is going to compress 3 dimes worth. Does that make sense? Well, yeah, more force here is going to compress it further. Well, let's see what they got in the book. They got 3.12. Now, the reason they got 0.12 is they rounded this number early. They rounded this to 1.186, okay? And by rounding off early, they introduced a little more error than we got. We got it more precise than they did. These intermediate steps, you don't have to round completely. It's only the answer you need to round. And so they got 3.12 times 10 to the minus 3 meters, which is 3.12 millimeters. All right. Does that make sense? I know I was using some magic there, but it really was legitimate. You see, my doing it my way got the same answer as they did. All right. Now, any questions on that? That's Hooke's law. They have a physics connection here about development of materials. It's a pretty interesting reading, but we don't have to do anything with it. They talk about the materials they use to build bridges and things like this. Originally they used wood and later went to stone. They talk about that, but then once they learned how to make steel, an American engineer, James Eads, which is pretty close to the name of the guy who's not here, he is Knees, but not quite the same, okay, constructed the first steel arch bridge over the Mississippi River, which was a pretty big river to do it. It was said not much stronger under compression than iron, but more than twice as strong as iron under tension and shearing stresses, because steel is a bit more flexible. So anyway, this is a picture in your text of a guy named Darby from England who built a cast iron bridge, which is pretty rigid, okay? And there's Darcy's, I think it is Darby's or Darcy, something like that, cast iron bridge that's still in use, and he built it back in 1779, so I'd say it had pretty good shelf life, okay? Now I bet you it's not holds, I'm just making a guess here, they probably don't put super a lot of weight on it, but they did put plenty. Now another thing is mentioned here. You may have heard them talk about pre-stressed concrete, and that's what they do here. They put tension on iron rods, pour the concrete around those iron rods, and when the concrete sets up, release the tension, and now the iron rods pull the concrete even tighter together, and that gives you what they call pre-stressed concrete. Because you see, concrete also is pretty brittle, okay? But if you put pre-stressed concrete, pre-stressed iron, that's called steel reinforced concrete, you get a stronger product, and that's what they're describing there. So now that we've done more problems in 12.2, you have more that you can do for homework. You can do any of the odds. We did number 1 in class, and if you weren't here to watch it, you can go back and see the thing on YouTube video when it finally loads. Probably won't be until tomorrow morning sometime, okay? I hope I'll get it moved over. But now you can do any of the odds 1 through 9, and then do any of the odds 11 through 19. Okay, and that wraps up our properties of solids. The main things to know: your stresses, force per unit area, and Hooke's law, which is force per unit length, is your Hooke's law constant, and how you use those. Now we're moving to properties of liquids, and some of these properties have very similar names to what you had for solids. Let me get the PowerPoint back. Last time it kicked me out of everything. Oh, this time it did better. And we'll move from current slide. That is our current slide. Okay. Let's see if there's anything in here. Oh, there was Darcy's bridge, or yeah, Darby's bridge. Darcy was Pride and Prejudice. Darby's bridge. Don't remember where it was. Coalbrookdale, England. Well, it sounds like that was a place they mined a lot of coal, so it probably did have a fair amount of weight on it. But that's quite a bit of cast iron that they have making these arches, so that probably could hold a lot. These columns here and columns here help support everything. Those, you notice, were made out of stone. Okay, so let's move on from there. And there's your steel reinforced concrete. Okay, you pre-stress the tension in the cables, pour the concrete around the cables. When the concrete dries, now when concrete dries, it tends to have little holes because the water that's dried out leaves some pores there. Well, when you then release the tension on the cable, that pulls that concrete together and you have a stronger product. So that's what they're talking about there. So let's move on to properties of liquids. And you remember these from solids. You have cohesion and adhesion. Cohesion is the property of like molecules or substances hanging on to each other. Cohesion, cohering with each other. Adhesion is dissimilar materials and their tendency to connect. Okay, so just as we had for solids, here it is in liquids too. Cohesion and adhesion. Now, one application of that is a principle called surface tension. Okay, now we aren't quite there ready for surface tension yet, but it is actually being illustrated here. Okay, see the water molecules, and if you remember, I mentioned before, water molecules have oxygen on one end and two hydrogens on the other end. The hydrogens tend to be positively charged, the oxygen tends to be negatively charged. So it makes what we call a polar molecule. One end is slightly positive, one end slightly negative. That's what makes water a liquid at normal temperatures and pressures. It ought to be a gas. As light as it is, it ought to be a gas, but those molecules really hang together. And that's what contributes to surface tension of water. Now you see the same thing happening here, but this is reflecting the fact that water also adheres to glass. And when you have water in a glass tube, if it's a small enough tube, you'll see the water actually climbs up into the tube. And the reason is the adhesion of water to the sides of the tube pulls it up there. But you see this container, water is adhering to that too. And here, and here. On a smaller tube, because it's a smaller diameter, it actually pulls it up higher. And then in a tiny little tube, and this is often called a capillary tube, it pulls it up even higher. Now this is probably somewhat of an exaggeration here for effects, that they're doing. But that's because water has that strong cohesion with other water molecules and strong adhesion with the, excuse me, I've got to sneeze, sorry. I hope I moved the microphone in time so it didn't blow your ears out. Okay. It must be getting cooler outside because I don't have a fan on and it's getting fairly chilly here in the room. But this isn't what this slide is talking about, but it does illustrate the cohesion of water and also the adhesion of water. This slide over here indicates mercury. And note, and by the way, this is called the meniscus, the curved surface that you have in a tube down here too. That's called the meniscus. Okay? With water, the meniscus is almost always upward. With mercury, it's almost always downward. And the reason is mercury does not have strong adhesion to just about anything, especially glass or plastic or things like that. Mercury is a metal, a liquid metal. It will adhere to metals, other metals, like any other kind of metal, but it strongly does not like to adhere to a plastic or glass or things like that. So now the meniscus is downward. So you have a big tube, it pushes that down just a little bit. A smaller tube pushes even further, and a tiny capillary tube pushes even further. That's the effect that mercury doesn't adhere to the tube at all. So therefore it's trying to avoid the tube. Now, I hope you haven't done this, but if you ever have spilled some mercury on a surface, you notice it gets in the little bitty balls. It look like they're solid balls until you touch them, but don't touch them. If you were to touch them with something, they are liquids, but they form a little ball because they don't want to adhere to anything. They're trying to get as far away as they can from any other object. And that's why they do these spheres, because that's the smallest surface area you can have, trying to get away from everything else. Water, on the other hand, covers it because it likes to touch the surface. Unless, of course, you have waxed the surface or there's oil on the surface. Then water will do the little spheres and try to beat up, because water and oil or wax aren't compatible, and water does not adhere to that, so it tries to form the little beads. And that's why when you wax your car, you'll have the water beating up on it and not coating the surface. That's more than they're asking for here. Okay, but there's surface tension. The figure they show in the book, and if we were in class we could do this. If you very carefully drop a needle into a little container of water, then the needle will float if you drop it in horizontally. Now you know that steel is denser than water. It should sink, but that surface tension of water is holding that steel needle up. Okay, now the surprising thing, if you drop just a drop of surfactant, meaning soap, liquid soap, Dawn, something like that, into that thing of water, bing, that needle goes down. Why? What a surfactant is, that's what I call it. A soap is nothing but a surfactant. Okay? You might say soap cleans your hands, right? That's why we put soap on our hands, it cleans our hands. Really not. What soap does is make the water wet better. Okay, now that sounds like a silly thing to say, but that's exactly what it does. It breaks that surface tension of the water molecules for each other. The soap molecules get in between, and therefore it wets better. And because water, remember, doesn't do well with grease, your hands tend to be, your skin has a certain amount of oiliness to it. And especially things if you're washing, dealing with frying or cooking something, you might get oil on your hand. Water would not do a good job getting that off. But you have a soap, makes the water break that surface tension, and now it wets better and washes away better. It's really not, soap is not a cleanser, it's a surfactant that depresses the surface tension of water, which has the same effect. Okay, and then here's what I was just sort of describing. Mercury will beat up on any surface unless it's a metal surface. The same thing's true of water. In air, water tends to make little droplets like that. Now, if you're out in space, it will make a perfect little sphere. If you're on the surface of the Earth, because gravitational pull of the Earth, that pulls the bottom part of the water molecule down and gives you that teardrop shape. And that's why raindrops are usually represented by that teardrop shape. If you're up there in outer space, it would be perfect little spheres. And those spheres would just float around in your spacecraft because they're not moving. All right, so that's one property of liquids. Or actually two. Not opposites, but similar things. Cohesion, adhesion. The second of these is viscosity. Now this is not something you talk about in solids, because solids don't have it. Liquids have viscosity. Viscosity is the internal, now all of you have books, right? Does anyone not have a book? I'll be glad to type these out for you if you don't have a book. Does anyone need me to type these out? Speak now. None? Okay. Sorry. All that sneezing I was doing is messing with my head. Viscosity is the internal friction, believe it or not, of a fluid caused by molecular attraction, which makes it resist a tendency to flow. Okay? Now, one of the prime examples of this would be honey or molasses. You've heard the same, slow as molasses. If you're trying to pour honey, especially if that honey is sort of on the cool side, it takes forever for it to run out of the container. Molasses the same way. Water, it just goes out. Okay? So honey, molasses are more viscous. They have internal friction that resists the ability to flow easily. That's viscosity. Now, where we practically use viscosity is in your car engine, because you know your car engine gets really hot and you want that car engine to be well lubricated, which means you're using oil. So you want an oil that has sort of a relative high viscosity, but not too high at cold temperatures, because the car is going to get really hot. You want it to still be able to lubricate at high temperatures. But if it's too viscous at cold temperatures, then it doesn't cover the surfaces because it resists that, and now you may have friction. So, especially in places like way in the north, I'm thinking Minnesota and places like that, their summers get almost as hot as our summers. In fact, sometimes they actually exceed the temperatures here. They're just not hot for as long. So they need in the summertime oils like we use down here in the south in their car engine. Okay, a fairly low viscosity, fairly high viscosity oil. Okay. However, in the wintertime, if they use those high viscosity oils, guess what? They get much colder than we do. And if you have too high viscosity, the oil does not lubricate well when it's cold. So they have to go with a lower viscosity oil in the wintertime and a higher viscosity oil, more like we use, in the summertime. So that's an example of that. And of course, when you heat it in oil, it becomes less viscous. Okay, so you don't want to get it too low of viscosity. The next topic or property of liquids is capillary action, and that's what these figures are showing. Capillary action is the behavior of liquids that causes the liquid level in a very small diameter tubes to be different from that in a larger diameter tube, like this. Very small capillary tube, the level will go up. Larger the tube, the more the level goes down. In this size area here, it's down almost at ground level, its normal level. Still crawls up the sides a little bit, but not very much. Now, mercury does not stay at the same level. It actually goes down because of the lack of adherence to mercury to the walls of the tube. So it actually pushes the mercury level down. But water, alcohol, other things like this, they usually are sucked up a tube. Now, am I right in guessing most of you are in some sort of medical field right now? Is that true? Generally true? I know you're going to a medical field. Have any of you either done this yourself or seen it done? Someone, say, who's testing their blood sugar or something else like that, might prick their finger with a needle, get a little drop of blood there, and sort of push out that blood, and then get what they call a very small pipette, which is a capillary tube, and hold near that drop of blood. Have you ever seen that happen? Psst, that blood goes right up the tube, doesn't it? That's capillary action. You see, the blood just gets sucked right up that tiny little capillary tube. Okay, that's why it happens. Capillarity. Okay, now that also results in other physical issues. Okay, I'm going to get into something now I don't think the book's quite going to get into, but let me tell you, just because it is fairly important. If you have a liquid or a fluid, that could be either a liquid or a gas, going through a constriction, okay, when the diameter gets smaller, the pressure, well, the velocity increases and the pressure decreases. Okay, now that almost sounds counterintuitive, but it's true. Okay, as velocity increases, the pressure decreases. Now I'm going to try to do the illustration of this for you here. Here's a piece of paper, and I'm going to try to get it so you can see it. I'm holding the piece of paper above my mouth. You see that? Okay, what's going to happen when I blow on the piece of paper? Make a guess. Anybody?
It's going to go up.
You're absolutely right, it did. Now I'm going to hold my mouth over the top of the paper. What happens when I blow over the paper? Guess?
Doesn't do anything.
Okay, watch. It went up again. That seems totally counterintuitive, doesn't it? Well, here's what was happening. When I hold the paper above my lips and blow, of course I'm blowing with more force on the bottom of the paper. It pushes it up. The pressure of my blowing on the paper pushes it up. But when I blow over the top of the paper, okay, what is happening, I'm making the air move more rapidly over the top, and that movement of rapid air over the top decreases the pressure on the paper, and now the paper rises. That's called the Bernoulli effect. Now, the reason I'm mentioning it here, here's the classic example of this in regular physics course. We would talk about a bird's wing or an airplane wing. If you happen to notice, they're shaped like this. They're big and bulbous here, and then they taper off to being small. Why a huge, heavy plane filled with hundreds of passengers can get off the ground is you have to go down the runway at a high enough speed, picking up speed until the airflow over the top of the wing is moving so much faster than that on the bottom, and there it's actually pushing up on the bottom because they're tilted downward, and the air on top has to go faster because it goes over the top of it, and that gives you what you call lift, Bernoulli's effect. So the lack of pressure on top pulls it up, the pressure underneath pushes it up. That's why the plane can take off. Okay, now let's apply that to human situation. If you have, this is a little bizarre, but if you have, say, hardening of the arteries, you got plaque buildup inside your arteries, the blood has a harder time getting through. Okay, it slows down, and when it slows down, the pressure goes up, and that leads to high blood pressure. Hardening of the arteries will go to high blood pressure. If that gets too high, you could have a stroke if it's in your head, a heart attack if it's around your heart. Slightly different things there, but you still have that going on. On the other hand, if you have sort of a ballooning of an artery, and that's often called an aneurysm, okay, now because you have a larger space there, the blood flow actually decreases again, and your pressure increases, and that's why if you have an aneurysm, you better have it taken care of because it could burst and you bleed out inside. Now that's kind of a wacko example, but that does happen. I was going to do something else with that, but I forgot what it is now. But I probably spent too much time on that. Let's move on to, I guess, the next slide. That was capillary action. And by the way, they now mention in the book what I did. The meniscus, okay, the meniscus is this curved shape in capillary action that pulls something up. It's a half moon sort of concave shape. If it's pushing down, that is a convex shape, and that's called your meniscus, that curved surface on whichever kind it is. And experimentally it's found liquids rise in capillary tubes, they tend to wet, and are depressed in tubes, they tend not to wet. The elevation or depression in the tube is inversely proportional to the diameter of the tube, and the elevation or depression decreases as temperature increases because there's less connection there, you might say. And then the physics connection here is oil viscosity. We've already talked about that. Let's move on to 12.4, which is properties of gases. Now this is a very, very short section. 4 paragraphs, very short paragraphs. One of the properties of gases, and it's also a property of liquids and solids, but it's much more pronounced in gases. Expansion is a property of a gas in which the rapid random movement of the molecules causes the gas to completely occupy the volume of the container. We talked about that last time. A gas is a material, no fixed volume, no fixed shape. Okay, liquid, fixed volume, but no fixed shape. Solid, fixed volume and fixed shape. Okay, now another property of gases, which is also true to some extent of liquids, certainly, and a little bit, but not too much on solids, is diffusion. Diffusion is the process by which the molecules of a gas, also liquid, mix with the molecules of a solid, liquid, or another gas. Okay? That's that same principle I was sort of talking about before. Open the lid on a bottle of ammonia, a perfume. They say a gas can. After a while you'll start smelling that gas because the gas molecules that are in the can start diffusing outward. Now I'm going to give you a little bit more precise definition of diffusion. Diffusion is the property that's caused by a concentration gradient. Now that sounds like a fairly complicated thing, but here's what it is. If you have large number of molecules per unit area in the can, small number of molecules per unit area outside the can, the molecules tend to diffuse outward because of the concentration gradient. Huge concentration here, low concentration here, they move from high to low concentrations. That's what diffusion is. I like to garden, okay, and I give this as a really dumb example of diffusion. Bermuda grass is one of my least favorite materials, okay, and Bermuda grass, if you have a flower bed, a vegetable bed, anything like that, the Bermuda grass is going to go from the area of high concentration, the yard, into your vegetable bed or your flower bed. That's the principle of diffusion. That's with a solid. Okay, so one other little definition here in gases. A fluid is a substance that takes the shape of the container, which means it can either be a gas or it can either be a liquid. Okay, so a fluid is either a gas or a liquid. The same principles for fluid flow govern what comes out of a pipe, what moves in your blood vessels, or the air coming out of a vent. Okay, that's all fluid flow. Air or liquid is a fluid. All right, now the next topic. Whoa! We just ran out of time. In fact, we may have run out of time a little bit ago, but I didn't look at my watch. Sorry. We will start next time with density, 12.5. Okay? Weren't any new problems in 12.4 or 12.3, but all your new problems were in 12.2, where we picked up from before. Next time we'll pick up with density, and density is a long section, a very long section, but that's the last section in the chapter. So when we finish 12.5, we'll be through with the chapter. That means it'll be test time for chapter 12. It means it's a good idea to be making progress on chapter. If you haven't turned in test 1, which all of you have, one person who's absent hasn't, okay, or test 2, and only 3 of you have turned in test 2, I think, so far. I may not have copied all of them because I'm behind in my printing, so you may have turned it in, but I haven't gotten it yet. I haven't printed it. But try to get those caught up before it's time for the test on chapter 12. Okay? Okay, Jalen? Yes, I graded it. I put it in my grade book, but I haven't put it in Blackboard yet. Yeah. Okay, is that Manessa? You said you're sending it in after class? Okay. I may pick it up in time. If the rain continues this weekend, I'm probably going to have time to get caught up on printing and grading. If it turns out to be a real nice day outside, I have a feeling I'm going to be outside working. But I'm going to try to catch up some this weekend. Okay? Not going out of town this weekend, so hopefully I'll get some stuff caught up. Good deal. Any other questions, comments? All right. We'll have a good weekend, meaning a safe weekend. A woman who's in one of my other classes, I don't know if I told you all this or not, maybe I did, her dad has been diagnosed with COVID. Okay, she's having to take care of him because her grandfather is quite ill, and the mother's having to take care of him, so the daughter's having to take care of the father. The trouble is they're afraid the father exposed the grandfather too, and so he may have it as well. He hadn't been tested yet, so it wasn't certain, but he had been hospitalized for a different matter and then came down with pneumonia after he got out of the hospital. They're afraid it might be COVID because that's a characteristic. So folks, it's around, it's real. Be careful, be safe. All right. Any other last comments, parting shots? Okay, I'm going to stop the sharing because I'm tired of sharing. Okay, and I'll end the recording unless somebody has an issue. Any questions, concerns? Okay, so I'll end the meeting for everybody. Take care. We'll see you next Tuesday.